So, good afternoon, everybody. Thanks for being with us. I'm sorry we cannot meet in Krakow, but we have a guest from far away from Gdańsk. So maybe you know Łukasz Rudnicki, who used to work in Warsaw at CFT. Then as a postdoc, he spent quite a few years in Germany, in few places. And now he is in Gdańsk, working at International Center for Technology of Quantum, for Theory, sorry, of Quantum Technologies, maybe for Technology of Quantum Theories. Maybe this works as well.
Could also be nice, yes.
And will tell us something about speed limits. So, you know, nowadays you are fined more if you violate the speed limit, especially if you go travel from Warsaw to Gdańsk, yes?
Yes.
So maybe we'll learn something more about it, how it looks like from the Gdańsk perspective, speed limits. Please, Łukasz, thanks for your visit.
Thanks a lot. So apparently, I will not tell you about this situation which Karol mentioned. On the other hand, I can tell you that I'm a bit afraid. I gave a very similar seminar 2 weeks ago in Poznań, also in online mode. And just after the seminar, I developed COVID. So look, I don't know how it will be today. I'm a bit afraid, but maybe it will not happen again. So let us see. Okay, so going to the content. So first of all, what I'm going to present today is rather conceptual. It should be a compact topic just to show you something and maybe to stimulate to some further like thoughts and ideas. So this is not so technical, not so long and deep. Is rather going to a particular point. The result which I'm going to describe, you can also find in this PRA paper. An interesting thing which I learned only in this with this example, which I didn't know, that when you have some paper in physical review, you cannot have a title which is a full sentence. So if you have a verb, then it doesn't work. And this means if you open the archive file, the title will be a bit different, will be helps interpret, because in fact, this is the idea. This and, which you can find here in black, like makes the meaning a bit fuzzy, when the proper idea of this very small project is that you use quantum speed limit, which is a very known, like, let's say, notion in basics of quantum mechanics, and you take geometric measure of entanglement, which is also well known, and then you try to use one to interpret the other and not just merge with n, but this is how it is. So you have two papers like the same, like two versions. In PRA is with end, and in archive you will find it with helps interpret, which is the proper way of thinking of the product. So I need to start with some introduction. An introduction is about quantum speed limit, of course, but here this is in the almost the most basic variant. As you can see, it dates back 50 years ago, more or less, when people started considering such a problem. And the problem was the following, because since there is Heisenberg uncertainty relation for many operators, especially for positional momentum, people also wanted to have a similar relation for energy. And of course, if you have energy, then you have time. So it should be for energy and time. On the other hand, this cannot work so easily because there is no operator corresponding to time. And this is because the Hamiltonian is bounded. Usually it's bounded from below, which means there is no operator for time, so to speak. This means there is no Heisenberg relation for these two notions, so energy and time. Still, it is clear there must be some interrelation. So somehow one notion can be bounded by the other and vice versa. And it seems quantum speed limit is exactly this concept which encodes that feature. What you have here is, as I told you, the most basic variant from many years ago, but surprisingly, or maybe not, very recently, there is a lot of research in this direction, expanding this field. For instance, people consider other distant measures, because as you already see, there is some distant measure here. By the way, can you see my mouse or not?
Yes, we do. We see.
But I will take like that. Now it's better, perhaps. Yes, okay. So you can see this is a distance measure, but this also means such inequalities, which I'll explain in 1 minute, can also be considered with other distance measures.
Yes, now it's much better.
What you can also see, there is a Hamiltonian, which I already mentioned. This, however, means that there can be like other kinds of evolution can be considered, open evolution with lambda generators. This is also considered very recently. The bounds are not so tight, but they encode some physics. This all is there, and this all can be found. And in a second, I will tell you where, if you want some overview. But now let us go back to this most basic case. And the most basic problem, which was considered in quantum speed limit topic, was the following: that we have an initial state psi, and we want to reach a final state phi. And we want to do this using unitary evolution. So evolution with some Hamiltonian. Of course, the states, they are not necessarily, they are distinct. That would be considered. It's not required, but we suppose they are distinct, which means the time to reach the other from the first one is not zero, but is finite. Then the question is how to bound this time. The inequality which you can see is exactly this one which tells you what is the minimal time tau which you need to go from psi to phi. This time depends on two quantities. So first of all, the variance of the Hamiltonian you will use to make this trip, and the distance between the initial and the final state. When you think about the variance, one needs to see that it's irrelevant whether this is calculated with the initial or the final state or any other state in between, because both states are connected with the unitary matrix generated by A, which means that when you compute the variance, that the value is time dependent. What is also important from a physical perspective, because this is what I would like to discuss more, is that in this inequality, you can find an energy scale which is hidden inside. Namely, if you have the variance, this means that if the Hamiltonian is multiplied by a constant, for instance, a larger frequency, then the variance which is here will be bigger, the time will be smaller, which simply means this time cannot be fixed, let's say, in absolute like values, but there is some unit of time given by the frequency. And depending on the frequency, depending on the energy scale, the time can be faster or smaller. So this distinction is sort of like in relation with the energy scale. Now, when we understand the phase inequality, we can look at the optimal Hamiltonian, because apparently there is a Hamiltonian which saturates this bound and is optimal for that. And the Hamiltonian is given by the initial state. It is sigma y. Basically, it's the sigma y Pauli matrix in the basis, which is formed by the initial state and the state orthogonal to it. And the state orthogonal is composed from the two states. So initial and final, we use Gram-Schmidt. That's how we get this state. So in the basis of these two states, we have sigma y matrix multiplied by the energy scale. And this is the optimal Hamiltonian. We will see in a moment how it works, but let me just tell you that if you really want to learn more about the basics of that topic and about very recent achievements in open system dynamics, which are with quantum speed limit, I can really recommend you this PhD thesis by Francesco. It was done in Australia last year. It is open access. You can upload it from the university. So this is accessible. Yeah.
By the way, so the author of the thesis was Francesco Campaioli, and in Monash, so who was the supervisor?
Cavanodi.
Okay. Yes. Good. So.
So this you can upload if you wish and check it. Everything is there. The picture is also taken from this thesis because it explains very well what is going on. And the point is that even though you have these two states, psi and phi, which are d-dimensional, and they are in this large space, CPD to the power minus d-1, still, we are only interested in those two states and a path between them, nothing more. And like regardless of the dimension, we can think about this, about the two-dimensional problems on the Bloch sphere.
Mm-hmm.
And then, of course, when we have these two states on the Bloch sphere, we have an orthogonal state, which is on the antipodal point of the previous one.
Mm-hmm.
And the distance which we have here is the Arcus distance here, which Carol likes a lot. So this is very clean from the perspective of this picture, and the Hamiltonian point in the y direction. All right, to understand that this is really saturating, because this is something which is not, this was perhaps almost never discussed in this quantum speed limit, because people were always happy with the inequality, but the fact that it can be saturated at this formally with this Hamiltonian is interesting to be observed. But it's also interesting for my further purpose, but to work with that, I would like to redefine something. Namely, I would like to define tau as a functional, which depends on these two states. So initial state and final state, which is transferred by the optimal Hamiltonian. And now this functional is simply Arcus cosine. So the distance between the two divided by omega. Why divided by omega? Because the variance of this optimal Hamiltonian is exactly omega. So this is the standard deviation. Variance is omega squared. So this is why the energy scale enters and everything cancels out. To see that this really forms the equality and not inequality, we can see what is the unitary operator generated by this Hamiltonian with this energy scale omega, and what we can see, this is the rotation with this omega t. But then this rotation needs to be applied in the basis psi bar, and after this is done, using this definition of tau, we get, yes, we get that this is exactly this form in this basis. So this is a 2 by 2 matrix in this basis psi bar in such a form.
I'm sorry, Łukasz? Yes. And all those results were not known before this thesis from Australia?
I would say the following. So Francesco couldn't find any reference to that. He even at some point cites geometry of quantum states as a general reference in which you can find what are the properties of all these distance measures. So this is what I know, and I also I never worked so deeply in quantum speed limit, but I was interested in that topic also many years ago, and from time to time I look at that, and I've never seen a paper discussing this, somehow because people were always fine with the inequality.
Yeah, no, because this looks very simple, but indeed it is not covered in our book. But of course, it looks very, very nice. Yes,
it is very simple, and but to be honest, I have no source for that. And I asked particularly, look, where is the source for that? I said, no, I couldn't find anything. So,
but look, it's also an optimistic comment that even you do not need to work too hard in mathematics. You can find very simple ideas and expressions which potentially are new.
Yes, this is true. Okay, so to continue, we have this matrix, and we react on the initial state, which in the basis is 1, 0. Then we multiply this coefficient by 1, so we have this one, and in the second it is coming from this part of the matrix, so this doesn't contribute because it's multiplied by 0 when we want to take phi. And then finally, if we remember what is psi bar, so we use this definition, we can see that the denominator cancels with that, the minus contribution cancels with that, and we are only left with phi. So this means this works. In such a way, we can close for a moment quantum speed limit and go to geometric measure of entanglement. This is one of many measures of entanglement, but what is let's say, nice with this measure is that it is defined for multipartite states and not necessarily with a predefined or fixed partition. So what we generally assume is that the state we are interested in is in a Hilbert space composed with k different subspaces. And using this fact, we can define k different or k-1 different measures, which tell us whether the state is entangled or not with respect to, let's say, onion kind partitions. So it can be separable, bipartite, tripartite, and so on, up to genuinely multipartite case. The definition is surprisingly simple. It comes from this very well-known paper. And this is also based on sort of a distance. So given a state, you look the closest state which is separable, or say M-separable, which means it belongs to a certain class of separable states. This means that if, and what to say, so if the state psi itself is M-separable, and this Sm is the set of M-separable states, then you can take psi equal phi, so this maximum is 1, 1 minus 1 is 0. In every other cases, this will be less than 1, and the measure is positive. This is how it works. Below, you can find examples if you want to understand better what this M-separability means. So for k equal 3, there is a fully separable state which has the product of 3, and they are biseparable states, which is decomposed differently, and can be also other permutations of that. But this is just to make a feeling what kind of structure we have here. Okay, so I've shown you the geometric measure of entanglement, and now I can put the question which I had in mind, namely interpretations of entanglement measures. And of course, there are interpretations which you can meet, or you could meet. Actually, this topic was more important 10 years ago than now. And then 10, 15 years ago, people were concerned with that, like deriving entanglement measures, all those discussions. Then they also wanted some interpretations. And for measures from that time, which are still used whenever necessary, you can find certain interpretations like success rate in some process, or exactly some distance. Or again, how much of a separable state we need to add to a state to get something. These are interpretations which are good from a probabilistic perspective, say formal mathematical, because you have a distance, but this is not the distance, this physical distance, it's in a matrix space. So it's the distance between like big matrices. Or again, success rate is another good probabilistic interpretation. You do something many times and you see how often you succeed in something. And then the entanglement measure which you have at hand tells you this probabilistic result. But the question which came to my mind was whether there are measures which have purely, let's say, physical interpretation more in terms of measurable quantities, like exactly like the physical distance, or some kind of mass, or some kind of time, something which is, or voltage, okay? How much voltage you need to do something. This is, perhaps this can be transformed, this interpretation, to something similar when one works sufficiently hard. But I don't think people usually considered measures in terms of this, say, more intuitive physical interpretation. And the question which comes when you look at quantum speed limit and geometric measure of entanglement is whether this is not the case. So whether these two, they do not form such an interpretation. So in particular, whether the formula with this for this tau for functional depending on the two states, initial and final, added, so to speak, to the geometric measure of entanglement, whether it doesn't provide this kind of interpretation. And then it is clear to understand it does, and it's nice to see in which way. And it does because of the following. So we have the functional, which we use in quantum speed limit. Psi is our initial state. and then we decide what is our final state. So usually in quantum speed limit, we decide this is a state which is orthogonal to the initial state, and this is why we answer the question how fast one can go from a state to an orthogonal state. And here we just change the question and we ask, what is the time we need to go from a state to the closest state, which is M separable. And this means that we take this final state to be M separable, and we minimize over all such states. So we look really for the minimal time, which means the closest state, which is M separable. And in such a way, of course, this time is 0 if the initial state is M separable, because we are already there. But if it's not in the set, then it needs some finite time to go to this set. Of course, we will always have the energy scale. This is something which we cannot avoid, because the more energy, the faster we are at our final destination. And this must be the case. So the omega, which is a free parameter of this consideration, must be there. But apart from that, we have this Arcus cosine now minimized. But the rest of formal consideration is quite easy, because the minimum of Arcus cosine is the same as Arcus cosine of the maximum. Is not the inequality, it's equal. This means that we have the geometric measure of entanglement, remembering that this is already part of geometric measure of entanglement in its definition. And after some manipulation, we have this result, or if we revert it in such a way, which means maybe looking from the biggest formula, that geometric measure of entanglement in terms of M separability is the sine square of the energy scale times the minimal time you need to have to go from your state to this set of M separable states. Maybe it's not fancy, but still I found it interesting enough to finish this project and to tell the people whenever they are interested how it works. The formula which you've seen so far is quite easy. This means that when you plot it, they are basically lines which are more or less the same kind of, but some with different rescaling of the argument. Still, they have this flavor that depending on the energy scale, the time is smaller or like bigger or smaller, so it's slower or faster. And the scale is there. So when you have 1 gigahertz, this is your frequency, then to go from the maximally entangled state to go to the state, let me check what we have. Yes, so now we don't specify M as an index. We say that this is going from state psi to some chosen by us state of M separable states. And then if the state is maximally entangled with respect to that state, and we want to go back to the state of this M separable states with frequency 1 gigahertz, we need 1.5 nanoseconds. So it is somehow linked with this time units and energy scale. And this is what is found here as a strict equality. What is also interesting is, because an immediate question comes, okay, this was for pure states, so how about mixed states? And this question is usual for similar problems. And then people often say, yes, it is possible, but it's very complex. You need to apply some construction like convex roof, and then you can generalize, but in practice, you know nothing, and so on. This is what people can answer usually. But this case is special, because an answer which comes immediately is that this result does not generalize to mixed states at all. And this is almost at all. I will tell you why almost. It does not generalize, first of all, because when you have mixed states, unitary evolution is not enough, because this means that the purity of all the states which are connected is the same. So if it means that the optimal state is with different purity, then they cannot be connected with unitary evolution. They need to be connected with other kind of open systems, say evolution. And then quantum speed limits for that kinds of setups, they are highly not sharp. So there are recent results. People know how to bound such time, but there is no hope to discuss optimality. And this means there is no hope to discuss equalities. There can be some inequalities. So maybe from these inequalities, there can be some bounds on entanglement measures, but I wouldn't say it's nothing. Perhaps one can work it out, but definitely there is no hope for some equality, even if one would wish to use purification and picture and some bigger unitary operators. I wouldn't say this is the way to achieve the goal. This is why this doesn't generalize to mixed states. It's for pure states, and it's rather conceptual than technical. And this was what I wanted to present you today. I promise my presentation will be very fast because I need to go soon, which I will show you. But there is still one topic which I wanted to remind using the opportunity that I'm virtually in Krakow. So if you replace 21 by 12, you go back 9 years ago to the moment when with Carol we were working on a very similar concept, with this was and is collectibility as some entanglement test. I could prepare new slides for that, but instead I took slides which Carol prepared that time. So this is precisely the slide from that time. And I will spend a couple of more minutes to tell you what collectibility was and how to link it with geometric measure of entanglement, because this is something which might be useful for someone. And in collectibility approach, this was our entanglement test. We did the following. Like in geometric measure of entanglement, the Hilbert space is composed of k different subspaces for simplicity of the same dimension. This was not required, but simplifies things. And instead of projecting the state on one separable state, we project on n different separable states, so the same number of states as the dimension. And the fact that we do this changes a lot, which I will show in a minute, but just to have some intuition, for instance, having k equal 4 and n equal 3, we can take one state in which for each particle we point up, another state where for each particle we point in the same x direction or in the same y direction. So this is not the whole basis in this big space. It's only part of the basis, a very symmetrical one, because each subspace has the same part of the tensor product. That's why we have n, not n to the power of k. But this is enough for our purpose. Then, if we take this object and use our definition, we can find that this quantity is generally bounded by n to the power of minus n. So perhaps one could multiply by n to the power of n to have it bounded by 1. So there is a general bound, but more importantly, the bound is much sharper if the state in question is separable, because then there is additional power of k which comes to the power, which changes a lot. This is because you take the product which I was showing you, you use arithmetic geometric measure like mean inequality, something sums up to 1, and depending on the state, either you have one term or k terms, and this is why the bound is such a small number comparing with the general case. It's interesting to say that for this kind of tests, maximally entangled states, they maximize, so they saturate this bound, and for more than 2, this is this VHZ state which does it. Yet another slide which now shows you again geometric measure of entanglement, but this is from 2012, so we have V instead of E. That's how we denoted it that time. And geometric measure of entanglement. Now we take the state for n equal 1, so we have the state of the set of fully separable states, and geometric measure is a distance to the closest separable state. So distance from the state to the closest separable state. And the question is, what happens for collectibility? For collectibility is sort of the other way around, because we have not one, but we have many separable states. So we are not discussing about this distance to a particular separable state, but there comes this collective effect. And collective is because if the state in question is entangled, then the projector which is in the measure is very small, is the smallest possible. On the other hand, for us, when the state is maximally entangled, the object which is inside our test is, which is the product of such different separable states is not the smallest, but is the largest, which changes completely the picture, and this is why it's collective and it's sort of dual to geometric measure of entanglement. I'm also telling that because, as I told you before, I had a very similar seminar in Poznań, and we are always very happy with Karol that many things in Poznań, but not only, happen in terms of this test. So I think in 2016 there was the first paper which measured this collective nonlinear witness, as they started calling it. And very recently, there are more and more papers which use it to, I would even say, fancy topics like entanglement witnessing with artificial neural networks. So the topic develops surprisingly well. If Karol Bartkiewicz, a different Karol, was not in Krakow recently, maybe it's a good option to let him describe this topic in the future. I would also be happy to listen about the details. And with that, with a summary, which was my major result, I need to tell you what I promised, because of course there is some time for a question, but I really need to run because Monday is the most difficult for me. So we need to go pick up the kids, and that's it. Thanks a lot.
Wow, thank you very much, but I hope you will still allow us for a few questions. So are there any questions? Markus, you are first. Yes, Markus?
I was just applauding, not raising the hand, but one of the questions is when you talk about the maximally entangled state, I think it even is not unique. So
yes, whenever it's not unique. Yes, whenever it's not unique, you have GHZ state as GHZ type state as the maximally entangled one in this topic. Yes.
Good.
Okay,
Thanks, Markus. Thanks for being with us. Any further questions? So maybe people will think about questions. I will ask a quick one. Of course, I'm interested very much concerning this mixed states business, which is more difficult. So we know how to compute the geodesic path in sense of the Bool's distance, also for mixed states. So now a question, of course, it will not give you possibly this smallest time, but is it okay, a good chance that this path Bool's geodesic will give you some answer or some bound at least? Yes.
Bound, yes. So I'm 99% sure that in the test of Francesco it's done. I mean, not geometric measure of entanglement, but the quantum speed limit for that distance, for the Bool's distance for mixed states. I think it's exactly discussed.
Yes, but the question was whether you get the minimal time if you follow the Bool's geodesic or not.
The bound, yes, but it's not optimal. I think it's not saturated. But the bound, but you can get a bound.
Yeah, bound, sure, but it will not be optimal. Following Bool's trajectory, it is not the optimal choice.
No.
So you can improve it in some cases, possibly.
Perhaps, but Francesco was working on that, and he rather moved to some other sub-directions. This means maybe it's not so easy.
Good, good. So last chance before Łukasz disappears to find his children. Who would like to pose the question?